Hi everyone, welcome to this episode of Kuiper Labs. Today we're going to be looking at connecting the properties of a substance to the arrangement of its particles. Okay, so far in the activities that we've been looking at, we've been able to, based on examining solids and looking at using 3D models to observe their structure, we've been able to look at three different classes of substance, or three different classes of solids. Okay, we've talked about atomic, molecular, and ionic substances. Okay, and we were able to distinguish those based on some different properties. Okay, that we could look at them based on the number, so key thing, so the number of elements present, so how many elements are there that we can see? Is it one or is it more than one? So that is it one only or more than one? So if it's two or more, it doesn't really matter too much because it can't be atomic, essentially. That's kind of the way we can knock that possibility out. And also, we're looking at the number of connections within and between particles. Okay, so looking at this idea of, is it basically all, some, or none, essentially. Okay, but so what we're now going to be able to do is let's dig into that a little deeper. Let's be able to actually connect and say, all right, well, we can classify a substance into one of these categories based on looking at models of its particles. Now we want to say is, all right, well, if the particles are arranged like that, what effect does that have on the way that substance behaves at a macroscopic level? Okay, so I'm going to take some time to pause the video. I'm going to set up a table that we're going to use and we're going to fill out as we go. Okay, so once it kind of pops up, take the time to set up the structure and then we will fill it in. Okay, so here we go. Here we got this table that I've put together. Clearly it's a little bit rough. I didn't have a ruler. My bad. But what I want you to do for me, so it's going to be 5 columns across and then 5 rows down. Okay, so make sure that you got your table set up like that. If you have access to a ruler, unlike me, please use one to make it nice and neat. But this is going to fill up pretty much all of a page. Okay, so I'm using a finer point marker to try and make it a little bit easier to read, or to be able to squeeze in things into the spaces. Okay, but so we've got 4 different types of substances that we're going to look at here. So I'm going to introduce some newer kind of terminology for you that we're going to be using here. So far we have looked at one of the types of substances we've looked at is ionic solids. Okay, so ionic substances. Okay, and then we've started to look at atomic substances. But what we've seen is that when we're looking at atomic substances, there can be a wide variety. And when we're thinking about solids, that things like argon and stuff like that aren't really good examples of those solids because you have to be super cold before they'll even stay as a solid. And we see that there's less concrete rules for something that's atomic than with, say, ionic or molecular, which is one of the other ones we'll look at. But we did see that one type of atomic substance exhibited some peculiar sort of things, and that was copper. And so what we're going to do is we're now going to see if we can try to explain, all right, well, why are metals the way that they are? Okay, and then we talked about molecular substances. Okay, but what I'm going to do is I'm actually going to add in a bit of extra terminology just for completeness for later, but we haven't actually established what this is for now. But I'm going to introduce the term covalent molecular because then I'm going to also introduce another type of substance that we haven't come across yet. Not directly, but we do need to be familiar with it. And it's called a covalent network substance. Okay, so I'm going to actually start at the bottom first, paradoxically, because I want to give you an example of each so you can kind of keep that in your mind. Okay, so for an ionic substance, we're going to think about sodium chloride. Okay, NaCl. Okay, so for metallic, we're going to discuss copper, Cu. Covalent molecular, we're going to discuss sucrose, which is, oh, getting ahead of myself, C12H22O11. And then covalent network substances, we're going to talk about diamond, okay, which is just carbon. And what we'll see is that it's a form of carbon that's different to soot, and it's different to graphite, which is also made up of carbon atoms. And the arrangement or connection of those carbon atoms is what gives diamond its particular structure. Okay, so when we look at the reason that we're going to focus on metallic solids is that they give quite specific properties that we're going to then kind of connect back to. What are the particles like? What types of particles do we have, and how are they connected? Okay, so let's start back at the top now, looking at melting and boiling points. Okay, so for ionic substances, we've got very high melting and boiling points. Lots of energy is needed to separate those particles from one another. Okay, because we looked at this idea that ionic substances have connections throughout. Okay, then our metallic substance, our copper, also had connections throughout. Our covalent molecular substance had some connections, and I'm going to suggest or put this idea that covalent network substances also have connections throughout. There is a T there, sorry, the reflection of the light. There you go. Okay, so very high melting and boiling points in ionic substances, and same sort of thing in our metallic. Okay, so metals having typically much higher melting points even then than ionic substances for the most part. Covalent molecular substances tend to have low melting points. Okay, so maybe around room temperature, maybe colder, maybe warmer, but nowhere near the levels of ionic and metallic substances. And then our covalent network substances, I'm going to even say extremely high. Okay, and so these ones are low, but I'm also going to add in variable. Okay, because it's not consistent between one type of substance to another. You know, sucrose example has a higher melting point, whereas ammonia or methane have very low melting points. So it's not a one-size-fits-all thing. Okay, so when it comes to electrical conductivity, so that ionic substances as a solid don't conduct, but when molten or in solution, okay, because remember that when it comes to electrical conductivity, that we need charged particles to be able to move to conduct electricity. Okay, and then when we have an ionic substance where the crystal kind of locks our ions together, as a solid, those charged particles can't move. However, once the solution becomes melted to this kind of oozing sort of liquid, or is dissolved in water, then all of a sudden those charged particles are able to move, so that then we can conduct electricity. We saw that with salt. As a solid, it didn't conduct electricity, but put it in solution, and it certainly did. Okay. So for metallic substances like copper, electrical conductivity is typically very high. Okay, so yes, definitely. So for covalent molecular, that we're typically thinking no. The only sort of examples, yeah, okay. So we would also then just tend to say no for covalent network here. Although I would add in except graphite. Okay, because of a peculiarity in the way that its structure is put together is that electrons are able to actually kind of work through the layers of graphite in a way that they can't in anything else. But say diamond, as our classic example, doesn't conduct electricity. Okay, when we're thinking about hardness, our ionic substances are very hard. And we would say also that they are brittle, okay, so that they will shatter. The idea and covalent network substances are the same, very hard and brittle. These are soft, and these we would use these words that you may have seen before: malleable and ductile. Okay, so malleable will be able to be hammered into sheets, ductile be able to be drawn into wire. That's so that we are yeah, so that they are malleable, so that their hardness can vary. Because you get metals like lead or sodium and they're quite soft, you get metals like iron and they're very hard. Okay, but so ionic substances are very hard and brittle because we have really strong connections between those positive and negative ions. And so if we try to change the crystal in any way, as far as if we try to squash it or we try to pull different parts in different directions, what happens is that very quickly the ions, the positive and negatively charged ions, which are kind of locked together, as it starts to kind of, if I kind of have it say like this, as the kind of the layers of the crystal start to slide away from each other, all of a sudden you get really strong repulsion between ions of the same charge. So they were locked together. As soon as it starts to deform or change in a way, it shatters and breaks. Okay, so that we can't change or squash the shape very easily. And covalent network substances are much the same. So with a covalent network substance, we're talking about connections throughout. We're talking about this idea of everything kind of being connected. And so if you try to change that structure, then it tends to break. But the reality is that substances like diamond are incredibly hard. So being able to actually do that, to make that happen, is not easy. Okay, but they're not, with the exception of graphite, not kind of soft and smushy or able to be changed in their shape. Whereas covalent molecular substances tend to be very soft. Okay, so low in hardness. So whereas metallic substances, their hardness can vary, but we can also change their shape and stretch them or change them into different shapes relatively easily. That's one of the benefits of metals, in terms of what we use them for. Okay, so we've seen with a table like this and some of my verbal kind of explanation that we can explain something about how the melting and boiling points, for example, and the hardness and electrical conductivity connect to the nature of the particles of a substance. Okay, we see that it then gives us an explanation as to why are melting points high in ionic substances but low in molecular. Okay, for example. All right, now I realize that we're just kind of scratching the surface, no pun intended, thinking about hardness of diamond, all that, but the idea being that I want you to start thinking and start digging into looking at how the connection and arrangement of particles affects macroscopic behavior. Okay, thanks very much for watching. Bye for now.